All right, so we're going to finish up this week by looking at section 3.5, which is kind of doing everything we've done before, finding roots, except now some of the roots might be imaginary. Everything we learned still applies. You can still use rational root theorem, you can still use synthetic division. Synthetic division with imaginaries it's a little harder because it's longer, but it's the same idea. So we'll look at it. Okay, so just repeating some of the stuff we've said almost every day this week. If you have a number that's a 0, that means you plug it into the formula, or you plug it into the equation, and the y value would be 0. Okay? That means that it's an x-intercept. So if you find a number that's a root of a function, you just found an x-intercept of the function. Well, let's look at something like this. If a polynomial does not cross the x-axis, then it doesn't have any real zeros, because the real zeros are where it crosses the axis. So if you graph something like y equals x squared plus 1, it's going to look, I'll just do it quickly like this. It's going to look like this. It's a parabola shifted up 1. Does it cross the x-axis anywhere? No, it doesn't cross the x-axis. That doesn't mean there isn't a number you couldn't plug in for x and get 0 for y. There is. It's imaginary. Okay? There is no real number that you could ever square and add 1 to and get 0 as the answer. Because any real number that you square is always 0 or higher. And if you take a number that's 0 or higher and add 1 to it, you're never going to get 0. Okay? So that's where you would have imaginary answers. And we'll look at that in a little bit. So when we deal with imaginary numbers, this is a basic definition that always comes up. I equals the square root of negative 1. If you ask me why is that true, I would say because. It's a definition. It's kind of like if you ask me how come parallel lines don't cross. Because. That's the definition. Parallel lines are lines that don't cross. It's just, that's how it's defined. I is defined to be the square root of negative 1. So what I basically allows us to do, even though I looks like a letter, and it is in the English alphabet, I represents a number in math. What number does it represent? That number right there, the square root of negative 1. So now if we just kind of extend that a little bit, if I is the square root of negative 1, and you take the square root of negative 1 and square it, what would you get? Yep. Right. The square and the square root cancel each other out, and what you're left with is what's underneath the root. So what that means is anytime you have an I squared in a problem, you should always change it to a negative 1. Okay. So that's kind of nice. I squared actually comes out to a real number when you do it out. So let's take I and plug it into the problem we just had and watch what happens. So I'm going to plug in I in place of x, and when you do I squared, what did we just say you get? Negative 1. And negative 1 plus 1 gives me 0. So that means I is a root of this equation. It's one of the roots. Whenever you have a complex root, they always occur in pairs. So if I is a root, I automatically know something else is a root. I'll tell you later on what that is. Right? But you never have a single imaginary answer. You always have two. Always come in pairs. Okay. Any questions on that? So we wouldn't say I is an x-intercept. You could say it's a root. You could say it's a 0. You could say it's something you plug in and you get 0 as the answer. You could also say, if I is a root, what would be a factor? What would you put in there? If I is a root, what would be a factor?
Minus I?
Yep. x minus I is a factor. Yep. And I'll tell you in a little bit, but the other root is x plus I. And I'll do this real quick, but if you FOIL it out, look what you get. X squared plus ix minus ix, and then negative I times I, negative I squared. Well, watch what happens if you simplify that. X squared plus ix minus ix. I squared is negative 1. What's negative I squared? Yep, positive 1. So what I just got right here is the original problem. Any questions on that? All right. So how did I know plus I was a root? If minus I was a root, it has to do with conjugates. Okay, and we'll get to that in a second. So complex numbers are always written in the form a plus bi. And the first number is the real, and the second part is the imaginary. So if I asked you in a number like this, what is the real part? You would say 2. If I said, what is the imaginary part? You would say 3. Okay, the I is just there to tell you what's in front of it is imaginary. So here's some examples of complex numbers. This one, the first one, and the second one are just pure imaginary numbers. And I think I write that. Maybe I don't. So these 3i and negative 7i are pure imaginary numbers because they don't have a real part. So if I asked you what's the real part for 3i, you would say 0. 0 plus 3i. There's no real part. 4, if you look at that one, you're like, wait, where's the I there? It's not there. So it's still considered a complex number. It's just the real part is 4. The imaginary part is 0. And usually when the imaginary part is 0, we don't write 0i. We just write the number 4. Okay, so these are all complex numbers. Sometimes the real part is 0. Sometimes the imaginary part is 0. Sometimes neither part is 0. Depends on the number. Okay, like here, the imaginary part is a negative 1. You can always put a 1 in front of an I, just like you could with letters. Okay. So two complex numbers are equal to each other as long as the real parts match and the imaginary parts match. All right, so if I gave you an example like 2 plus 5i and 2 plus 5i, those are equal complex numbers. Now, if I said 2 plus 5i and 2 minus 5i, you look at it and you're like, well, the real parts match. Yeah, but the imaginary parts don't. So you wouldn't say that, well, they're half equal. No, they're not equal at all. Okay? For two complex numbers to be equal, you got to have the real parts match, and you got to have the imaginary parts match. All right, so when we're doing arithmetic, add, subtract, multiply, divide, you basically can treat I like a letter. Okay, in terms of like combining like terms. So like 2i plus 3i is just like doing 2x plus 3x. 2i plus 3i, 5i. 2x plus 3x, 5x. Okay, but I want you to remember, I is not a letter. You can treat it like a letter, it's not a letter. Okay, it's kind of like in math if you said this is a letter. In math, no, it's not. In Greek, Greek alphabet, yeah, it's the letter pi. But in math, that letter stands for 3.14. Well, I is a letter in the English alphabet, but it stands for square root of -1. So keep that in mind. I is really a number. When we multiply, I kind of already did this for you. when I did some foiling earlier, you're going to end up with a lot of I squareds. Well, not a lot. Usually it ends up happening in one spot. Anytime you get an I squared, always change it to a -1. When we do division, big thing with division is you're not allowed to leave a complex number in the denominator. So if you had a final answer like this, it would be marked wrong, because no matter what the problem was, you should never leave I in the bottom. Ever. Okay? So there's a way to fix that, and that involves a conjugate. And then let's look at what happens when we have square roots of negative numbers. Well, what number is in front of x there, even though it's not written? Yeah. Right, there's a -1. And remember, when you have a product under a root, you can separate it. Right? If you had the square root of 3 times 4, you could make that the square root of 3 times the square root of 4. Well, if you've got the square root of -1 times x, all right, well, actually, I'll just leave that for the second step. So put the -1 in front. Now separate it into 2 roots. Square root of -1, square root of x. And this, we have a way to simplify. What's the square root of -1? Yeah, I. So basically what ends up happening is anytime you take the square root of a negative, you pull an I out, and then you just do the square root like you would normally. But you just have to put the I in front because of that negative symbol right there. Now, I'm going to show you a couple different examples, and we'll see what happens. Okay. Let's try the square root of, let's do square root of -7 first. Okay. How would you write the square root of -7 without a negative under the root? Yeah?
I squared to 7.
Yeah. I square root of 7. Now, square root of -4, that one's a little different because you can take the square root of that number and get a nice answer. So when you're done, you're not going to have a square root in the final answer. So does anyone know how we would write that one? Yeah.
2i.
2i. So if you're saying, well, wait, why did he put the letter after the number when he just said to put it before it? Because when you can take the square root, it's okay to put the letter after it. If you put I2, I mean, that's okay. Most people don't write I2, they write 2i, but that's fine. The reason why we don't put the I after the root is because, look at this. That looks confusing to me. I'm not sure there if the I is supposed to be under the root or if it's not under the root. So if you just take the I and put it in front, there's no confusion at all that the I is not under the root. That's why we put it in front. Questions on that? Okay. So let's look at square root of -9. What would the square root of -9 be? Yeah.
3i.
3i. And now square root of 20, well, you treat it just like it's the square root of 20, but then your answer has an I in it. Right? So if I was going to break it up, I might think of it this way. Square root of -1 times square root of 4 times square root of 5. Square root of -1 is I. Square root of 4 is 2. Yeah.
I was going to answer.
Oh, you're going to answer, sure.
It would be 2i squared root of 5.
2i square root of 5. Yep. Again, okay to put the I right in between there because that way it shows it's not under the root, and that's probably a better way to do it. If you wrote this, is this wrong? No, you could write that, and it's pretty clear that the 2i is not under the root because I used parentheses, but that's more standard. All right. So now we'll go through and add, subtract, multiply, and divide real quick. So add. Just think of it as combining like terms. Combine the reals with the reals, imaginaries with imaginaries. So Jacob, what's the real part of the my first parentheses?
7.
And the second parenthesis, the real part?
4.
And if you add 7 and 4, what do you got? 11. So in my final answer, the real part is 11. Natalie, what's the imaginary part in the first parenthesis?
-3.
And in the second parenthesis? 5. If you add negative 3i and 5i, what do you get?
2i.
2i. That's it. That's how you add. Okay? Just reals to reals, imaginaries to imaginaries. Subtracting is the same idea, except you want to think of that negative as being distributed. So you're subtracting 6 and you're subtracting an I from the first part. So Emily, if my real part here is 4 and I'm going to subtract 6, my final answer would have a real part of -2. So yeah, -2. And now I've got -2i minus I. That's the part people mess up. Okay, so -2 minus, or -2i minus I. What's -2i minus I? Yeah.
-3i.
-3i. Okay. And that's it. That's subtracting. Okay, so adding and subtracting, pretty straightforward. Let's look at multiplying. Okay. Don't mix that up with adding or subtracting. If you see a plus or a minus sign between the parentheses, then you add or subtract. If you don't see anything, then you're foiling or double distributive. So let's distribute it out and see what we get. Robin, if I do my first foiling, 2 times 5 would give me 10. The next part?
-2i.
Yeah, -2i. Okay, how about, Gabe, how about 5 times 3i? 15i. Yep. And 3i times -i. Well, the first thing I think of is, all right, it's a positive times a negative. Positive times negative is negative. What's 3i times I? Yeah.
3i squared.
3i squared. Now, a few things we need to do. There's some like terms. -2i and 15i. And there's -3i squared. Well, let's start with I squared. We'll just write it up above. What's I squared again? What number? It's -1. So this last part is minus 3 times -1. What's that going to be? Yeah. +3.
Wait, so you're just putting -1 in for the I?
I squared.
So -1 minus -1 would be positive 1.
Well, this whole thing, I squared equals -1.
Oh, okay.
So you're not plugging in like a -1 for
Okay.
I. You're plugging in -1. You're simplifying I squared. Okay? So I squared is -1 times a -3 is a +3. Just a coincidence, the real part and imaginary part came out the same. So it's 13 plus 13i. Knowing how to FOIL or distribute is important because that's how you have to do division. Right? It's going to involve multiplication. So in order to divide, we have to know what a conjugate is. So the idea of a conjugate is you just change the sign of the imaginary part. So if you had a number a plus bi, the conjugate is a minus bi. You don't do anything to the real part. Just change the sign of the imaginary part. So if I had 3 plus 2i, can someone tell me what the conjugate would be? Like
3 minus 2.
3 minus 2i. If I had 4 minus 5i, what would the conjugate of that be? Yeah.
Plus 5i.
4 plus 5i. Okay. If I had 3i, what would be the conjugate of that one? Yep.
Would it be -3i?
Negative 3i. So you could think of that as 0 plus 3i. The conjugate is 0 minus 3i. 6. What's the conjugate of 6? Yeah. 6 stays the same. If you're like, wait, aren't you supposed to change the sign? Nope, not for the real part. Think of it as 6 plus 0i. The conjugate is 6 minus 0i. Plus 0 minus 0, same thing. Okay, so those are conjugates. So now, I'm going to show you how to use a conjugate with division, and that's going to end kind of the quick review of complex numbers. So whenever you want to divide two complex numbers, like this, you multiply the numerator and the denominator by the conjugate of what's in the bottom. And remember what I said, you're not allowed to leave I in the bottom? That's what the conjugate is going to automatically fix. If you do it correctly, all the i's are going to disappear from the bottom. Okay. So to divide, multiply the top and the bottom by the conjugate of what's in the bottom. So the conjugate of what's in the bottom is 2 plus 3i. 2 plus 3i. Now, doing it really quick in my head, I know the answer is 13 when I do the bottom out. I'll show you the long way, and then I'll show you how I got 13 for the bottom, doing it in my head. All right, let's do the top first. So we've got 5 times 2, and now I've got 15i plus 2i. I'm going to combine those as I go. What's 15i plus 2i? Yep. 17i. And let's see if we can do something here. Positive I times positive 3i. That's a positive 3i squared. But what number is that? 3i squared. Oh, right?
Negative 3.
It's negative 3. Yep. You don't have to do that. You can write it down and do it in several steps. I'm just doing it that way. Now, watch what happens in the bottom. 2 times 2 gives me 4. 2 times 3i is how much? 6i. What's 2 times negative 3i?
Negative 6i.
Gone. They cancel out. That always happens when you FOIL conjugates. The i's always cancel out. That's the point. So 6i minus 6i. Now I've got negative 3i times positive 3i. Well, negative times positive is negative. 3 times 3 is 9. I times I is I squared. So in the top, I'm going to get 7 plus 17i. Now in the bottom, I have 4 minus 9i squared. What's minus 9i squared? What number is that, Robin?
Positive 9.
That's really a positive 9. 9 plus 4, there's the 13 that I mentioned when we started. Now, the only thing you have to do is we generally don't leave it like that. That's not standard form. Standard form is real part and then a separate imaginary part. Bless you. It's not really a big deal just to go from the last step to this step. You just put each number over the denominator separate. So 7/13 plus 17/13 I. Now, if this was like 7/14, I would reduce it. Okay, but 7/13 I can't. Now, the quick way I did that in my head, look at the first number, square it. You get 4. Look at the second number, square it. You get 9. Does it matter if you use the negative or not? Nope, because if you use the negative, it just cancels out. Square that number, and add them up, and that's how you get the bottom. So if you wanted me to multiply like 5 plus 6i and 5 minus 6i real quick, I would say 25 plus 36. I would add those two numbers up and get 61. If you don't want to use that little shortcut of squaring the real part, squaring the imaginary part, just the numbers, not the I, just the numbers. You don't have to. You can FOIL it every time, but you're always going to get like a plus 6i minus 6i. You're always going to get something in its opposite. It just cancel. Okay? So if the shortcut's confusing, maybe just stick with FOILing it out and canceling stuff out every time. Right? But any questions on that? Okay, that's a quick review of complex numbers. Now let's look at the same kind of problems we've been doing all week. Let's find the zeros of this function. Normally I would say, well, let's use the rational root theorem. Let's make a list of possibilities and graph it and do all that, but we don't need to. It's a quadratic. We already have a built-in formula to solve any quadratic problem. So let's just use quadratic formula. What's A in this case?
1.
1? How about B?
1.
And C?
1.
How exciting. So A, B, and C are all 1. Let's see what happens when we plug it into quadratic formula.
Negative 1 plus or minus the square root of 1 squared. 1 squared minus
I did 1 squared. I just
4 times 1 times 1 over 2.
Yep. So you can already see we're going to get an imaginary answer. 1 minus 4 is negative 3. So I get negative 1 plus or minus the square root of negative 3 over 2. Now, we should probably simplify the square root of negative 3, so there's no negative under the root. And what would we do for that? Yep. Yep. So we're going to write it as I square root 3 over 2. Those are your two answers. If you want to write them out in standard form, it's negative a half plus or minus root 3 over 2i. That's standard form. That's exactly the same thing that I have up above. It's just standard form. You got to have real, imaginary, and then an I next to it. Any questions on how I took this and turned it into that? Yep.
Why isn't the I over 2?
Because when you have, like, let's just pretend I was a number. Let's say we had 3 times 5 over 2. It's exactly the same as writing it this way. Doesn't matter if you put them both over 2 or not. You're going to get exactly the same answer. Or even if you did it this way. 3 times 5 over 2. You don't have to put the whole thing over 2. I'll do it real quick. 15 divided by 2 is 7.5. That's 1.5 times 5, which is 7.5. 2.5 times 3, 7.5. So, any other questions on that? Okay. So if you look at, just go back for a second, look at the answers here, they're conjugates. Negative a half plus root 3 over 2i, negative a half minus root 3 over 2i. That always happens. So if I tell you that a plus bi is a root of a polynomial, then a minus bi is automatically a root. Always. So if 2 plus 3i is a root, 2 minus 3i is a root. Complex or imaginary roots always occur in pairs, specifically conjugate pairs. So when you're solving a problem, you will never have an odd amount of imaginary answers. It has to be even. It has to be. And of course, this is assuming that b isn't 0, because if b is 0, you just wipe that part right out. Now you're not dealing with imaginary numbers at all. It's real. So the remainder theorem, the factor theorem, synthetic division, it all still works with complex numbers. All right, so I'm going to pick out one to try, and I want to prove that something is a root, but I'm not going to do that one. Let's do. And I don't have a better one to do, so we're going to do it. We're going to show that 1 minus 2i is a root, or is a 0. Now, what's that the same as showing? If 1 minus 2i is a root, I could show that, what else? It's one of those statements we mentioned earlier. It's not an x-intercept. That's not going to work here because that's imaginary. But if 1 minus 2i is a root, what else do I automatically know? Yeah?
That 1 plus 2i is a root.
Okay, so yes, that is true. If 1 minus 2i is a root, 1 plus 2i is a root. But what if I said to you, like, 3 is a root? If 3 is a root, then what is a factor? Yep.
X minus 2.
X minus the root. Whatever the root is. So if 3 is a root, x minus 3 is a factor. If 1 minus 2i is a root, then x minus 1 minus 2i, could use parentheses, is a factor. I'm going to show that that's a factor. And now to show that this entire thing is a factor, I'm going to divide it in using synthetic division and hope that I get a remainder of what? Yep, 0. That's the goal. So we're going to do this exactly the same way. On a test, I would probably give you one that's cubed, because 4th degree is going to take a little extra step. But let's go through it and see what happens. So put your root on the outside. Fill in all your coefficients. 4, be careful, you're missing the cube term. So 4x to the 4th, 0x cubed, 17x squared, 14x, 65. It doesn't start off too bad. So you bring down the 4, and now you multiply 4 times 1 minus 2i. That's just a distributive property, like that. So it's 4 minus 8i. Any questions on that stuff? Now, what do I do with the two numbers in that column? Yep. I add them. That's not bad because it's a 0. In fact, the adding piece is never that bad. Now, this is the part that gets a little annoying. You have to multiply this times that. Not that it's hard, but we're going to have to do it a couple times. So let's do it out. And I'll do it off to the side so I don't mess up the problem we're doing. So 1 times 4 gives me 4. 1 times negative 8i. Negative 2i times 4. And what's negative 2i times negative 8i? So negative 2i times negative 8i. Yep.
16i squared.
16i squared, and I squared is
-1.
negative 1, so it's minus 16. So when I multiply these together, I get 4 minus 16, which is negative 12, negative 8 minus 8, negative 16i. And now add your columns. There's nothing to add with the I. How about 17 plus negative 12? Yep. Plus 5. Now we got to distribute it again. So we've got 1 times 5. I've got 1 times negative 16i. Negative 2i times 5. And then what's negative 2i times negative 16i squared? Yep. Yeah.
32i cubed. No.
32i
Negative 2i negative. Will be squared?
squared, because it's just an I to the first times an I to the first.
Oh, I thought you said I squared.
Oh, I might have, I'm sorry. Yeah, it should just be 32i squared,
Yeah.
which is negative 32. Okay, and now put that answer here, and then we should get a nice answer. We're hoping to get 0 the next time we do this. We'll see. So, 5 minus 32 gives me how much? Yep. Negative 27. Not the nicest number. And then negative 16i minus 10i is negative 26i. Add your columns. What's 14 plus negative 27? Negative 13. But if I remember correctly, this is working out exactly the way it should. On a test, you'd be done right here. Okay, I'd give you one less column. We got one more to do because I couldn't find a shorter one right on the spot. Okay, so now watch what happens here. We get 1 times negative 13, 1 times negative 26i, negative 2i times negative 13. Negative times negative is positive. 2 times 13 is 26i. That's good. Negative times negative is positive. 2 times 26 is 52i squared. Negative 26i, positive 26i. Gone. What's 52i squared? What number is that? Yeah. Negative 52. And what's negative 13 minus 52? Negative 65. Remainder is 0. We just proved that 1 minus 2i is a I proved x minus the root is a factor, which means the root is, we confirmed that it's a root. Okay, so if you prove that x minus the thing is a factor, then you prove that that thing is a root. Whatever comes after the minus sign. Okay, so a little annoying with synthetic division. You'd have one less column on a test, but still not super bad, just kind of a little time consuming. Any questions on that? Okay, so odd degree polynomials always have to have one real 0. That's the same as saying they always have to cross the x-axis at least once. Why? Why would an odd degree polynomial always cross the x-axis at least once? Yep. Okay, it always goes up and down. And what else about polynomials? What kind of functions are they? Just because something goes up and down doesn't guarantee it goes through the x-axis. Here's a graph that goes up and down forever, but never goes through the x-axis. Yeah? It's continuous. So odd degree polynomials will always contain at least one real 0. Why? Because they are continuous and the end behavior is either one of the following: down up or up down. If something goes up and down forever, whichever end is going up and down, and it's continuous, it has to pass through the x-axis somewhere. So now this exponent tells you how many answers the problem is going to have. There's going to be 3 answers. So in this kind of problem, let's think about like the different scenarios that could happen for real and imaginary. Could it cross the x-axis in 3 spots? Yes, and if it did that, that would mean you have 3 real answers, no imaginary. We just said you could have 1 real. Could you have 1 real and 2 imaginary? Yep, that could happen. Could you have 2 real one imaginary. What did I say about imaginary answers? Why not?
Because you have to have two imaginary answers.
Imaginaries come in pairs. So you could never have two real, one imaginary. It's not possible. These are the only scenarios that could happen. Now, when I say three real answers, I'm not saying that they're all distinct. You could have something like this. And if you FOILed all that out, that would only cross the x-axis one time. It would cross the x-axis right at 2. But the other two answers are not imaginary. They are just repeats of the same answer. That's where looking at a graph can get a little tricky. All right? So this is a problem where it only crosses the x-axis once, but there's a triple root at the number 2. Okay? But no imaginaries. So now we'll look at our problem. Yep.
What do you call those numbers?
X minus 2, x minus 2, x minus 2.
The numbers, the real and imaginary ones.
Because the highest exponent tells me how many solutions I'm going to have. So on each row, they have to add up to 3 solutions. When you combine all your real and imaginary answers, you've got to have a total of 3.
So how would you know that the real doesn't, like, in the first one the real is 3 and the imaginary is 0? How would you know that it doesn't get swapped over, that the real is 0 and the imaginary is 3?
How come you could never have a 3 for imaginary? Yep. They always occur in pairs. So you could never have 0 and 3. Because then you'd have an imaginary root that's not paired up with its conjugate. So this column always has to be even numbers.
Okay.
It has to be even. You could have 2, you could have, well, in this problem, you could only have 2. Right? And you can't have 1 because that's not an even number. So 0 and 2 are really the only options. So let's see what happens here. We got x cubed minus 1. In order to find the roots, the first thing we have to do is we have to turn this into a quadratic. How do you turn it into a quadratic? You find a root using the rational root theorem, divide through by it, and then your quotient will be a quadratic. So let's find a rational root. What are my factors of p here? Yeah. Plus or minus 1. The factors of q are plus or minus 1. So now, if I have a rational root, it's of the form p over q, which is just plus or minus 1 divided by plus or minus 1. So not very exciting. Does anybody see what number, if you plug it in there, would work and give me 0 without me even graphing it? 1. 1 is a root. If you didn't see that, you could graph it. But if you plug in 1, 1 cubed is 1, take away 1 is 0. So that's an easy one. You really don't need a calculator to narrow down the list of possibilities. If you try negative 1, it doesn't work. If you plug negative 1 in, cube it, minus 1, you don't get 0. All right, so now we know 1 is a 0. 1. And let's see what else is 0. So once you find a root, divide through synthetically by it. If at all possible, I always try to find a root that's real, so I don't have to do synthetic division with complex numbers. I don't like to do it, so if I can avoid it, I usually do. So we've got 1, and then what would my exponent, or what would my coefficients be on the other side? Robin?
1, 0, 0, 1, or negative 1?
1, 0, 0, negative 1. And this is going to be super fast synthetic division because we got all 1s and 0s. So bring down the 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. Negative 1 plus 1. We already knew we would get a remainder of 0. And now there's my quotient. Right, so now x squared plus x plus 1. We're going to solve for the roots here. So we just took our cubic, x cubed minus 1, down to a quadratic, by using a root we found from the rational root theorem. But now this, we've already done this problem. X squared plus x plus 1. I did that one right here. Find the roots of x squared plus x plus 1. So I'm not going to go through the whole thing again. But the roots are negative a half plus or minus root 3 over 2i. So negative a half plus or minus root 3 over 2i. So this case was that. You have one real, two imaginary answers. And they occur in conjugate pairs. The negative 1/2 plus root 3 over 2i comes from example 4. So you would now have to do example 4 to finish off this problem. So I'm just going to put C example 4, and that's exactly the problem we already did. Okay. Any questions on that one? So approach is the same. Rational root theorem, synthetic division, maybe a graphing calculator if you need to. Sometimes you don't need it. Alright, so let's look at this. So in example 6, 0 equals x cubed minus 1. That's basically what this says. We found the roots. 0 equals x cubed minus 1. Well, if you add 1 to each side, you get this. To solve that problem, right, if you were thinking about it from like an Algebra 1 point of view, if the person knew what they were talking about, they would tell me to take the cube root of each side. Well, that's basically what we did. In the last example, we solved this problem. We found all the cube roots of 1, and there are 3 answers. If you cube 1, you get 1. If you cube negative a half plus root 3 over 2i, you get 1. If you cube negative a half minus root 3 over 2i, you get 1. Okay? These are all the cube roots of 1. And sometimes the book refers to the number 1 as unity. So finding the cube roots of unity, I usually just say finding the cube roots of 1. So if you set up any equation where you have x to a power minus 1 on one side by itself, and you have 0 on the other, think of this equation like this. X to the nth equals 1. Well, to solve that problem, you would think, oh, take the nth root of each side. So solving this equation gives you the nth roots of 1. And whatever n is, that's how many answers you should have. If you're doing square roots, you should have 2. If you're doing cube roots, you should have 3. If you were doing fifth roots, you should have 5. Okay? So whatever root you're taking, that's how many answers you'll have. Right, and we're going to try another example. So we just did the cube roots of 1. Now we're going to look at the fourth roots of 1. So how many answers should I be expecting to get here? 4 answers. Well, I already know 1 and negative 1 are answers. I could use that to my advantage, but let's just go through it, pretend that we couldn't figure out any of the roots in our head, beforehand. So I'm finding the fourth roots of 1. So fill in 4 for n. So x to the fourth minus 1. Now, normally what I would say to do is use the rational root theorem, find a root, and if you did that, you would discover that 1 is a root. Divide through synthetically by 1. You would turn this quartic into a cubic, and then you could find another root, a negative 1, from the rational root theorem, and divide again, you could turn it into a quadratic. But that's factorable. So you don't have to use any synthetic division if it's factorable. We can avoid everything I just said, as long as you can factor that. That's a difference of 2 squares. You can square something to get x to the fourth. You can square something to get 1. A difference of 2 squares is always factorable. Does anybody see how that would factor? Yeah?
It would be x squared plus 1, x squared minus 1.
Yep. Now, if you had done what I just said, use the rational root theorem, divide through synthetically, use the rational root theorem, divide through synthetically again, you would have turned your quadratic, or your quartic into a quadratic, you would have gotten that. That's what you would have gotten if you did synthetic division twice. But by factoring, we can jump right to it. If you can't factor, then you got to do synthetic division. Now, x squared plus 1, you can't really do anything with that. But that's another difference of 2 squares. So how does x squared minus 1 factor?
X plus 1, x minus 1.
X plus 1, x minus 1. Now set all of those factors equal to 0, solve, and those are your roots. So here, you get x equals negative 1. Here, x equals positive 1. Now let's look at this one. X squared plus 1 equals 0. X squared equals negative 1. How do I undo squaring? Yep, Chris.
Square root.
Take the square root. And remember, when you take a square root, how many answers are there? 2. There's the positive and the negative square root of negative 1. But we know the square root of negative 1. What's the square root of negative 1? Yep. I. Plus or minus I. So if you wanted to know what are the fourth roots of 1, I, negative I, 1, negative 1. And notice they occur in pairs. Plus I, minus I. Always going to pair. Not too bad because we could factor. Synthetic division, it would have probably taken us at least twice as, maybe 3 times as long as it just took us here. But generally, I wouldn't give you a problem and ask you to do synthetic division with it if there's a shorter way to do it. Right? So if you start getting into a problem and it looks like, man, this is awful, it's probably because there's a shortcut and you're not seeing it. How do you see it? Well, you just have to be good with factoring. And it wouldn't be anything more difficult than something like that. If it's factorable and you know how to factor, it should be obvious. All right, so this idea I've already mentioned to you, that the number of answers that you get in a problem is equal to the degree of, is the highest exponent, the degree of the polynomial. All right, so if you look back at examples 4 through 6, that always happened. Total number of answers equals the degree of the polynomial. And there's 2 theorems that the book mentions about this. The first one is the fundamental theorem of algebra, which basically says that if you have a polynomial that's not a constant, okay, at least linear or higher, degree 1 or higher, and the coefficients are real, then you're always going to have at least one complex 0. Which doesn't really tell you a lot. Of course you are. If you're solving a problem that has an exponent of 1 or higher, you're always going to have 1 or more answers. That's all that that's saying. And when it's saying complex, complex doesn't necessarily mean it has an imaginary part. This is a complex number. So all of that theorem really says is that if you solve a problem higher than degree 0, you're going to get more than 0 answers. It's not really that helpful. But I mention it because they mention it in the book. This is the theorem that's more important. It's more specific. It says that if you solve a polynomial where the degree is not a constant, anything higher than a constant, then if you want to factor it, it will factor into as many sets of parentheses as you have the highest exponent. If the highest exponent is a 3 and you want to factor it, 3 sets of parentheses. If the highest exponent is a 5 and you want to factor it, 5 sets of parentheses. Now, how would you figure out how to factor something like this? At this point, I've taught you what you need to know to factor a problem like that. You have to use the rational root theorem. Look at all your factors of 6, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, and you would have to use synthetic division twice. Okay? Get a root, confirm it on the calculator, divide through synthetically by it. And actually, you know what? If you just did it once, it would turn into a quadratic, and then from there, you'd be able to factor the rest of it. So I take that back. You'd only have to use synthetic division once. But because it factors into nice numbers, you should be able to factor something like that now, as long as the numbers are nice. Okay? So I've got to give you a problem where the rational root theorem works. If I don't do that, then you can't factor it. The roots don't need to be distinct. Okay? So if this was a 5th degree polynomial, you might say, well, it only factored into 2 different factors. That's fine. Factors can repeat. Right? So if I were to graph this, even though it would be an x to the 5th power, if I FOILed it all out, this only crosses the x-axis in 2 spots, -1 and +2. And I didn't write it down. But the way you can say it is you can say -1 is a double root, or you can say -1 is a root of multiplicity 2. Just means it occurs twice. 2 is a triple root. It occurs with multiplicity 3. 2, 2, 2, 2. So it's a root or 0 of multiplicity 3. Any questions on that? Okay, so it was a kind of a really quick overview of complex numbers, but then trying to show you how synthetic division and the stuff we learned this week still applies. Okay, so that's the homework for tonight. And for the test tomorrow, some things that you probably want to know how to do are find roots using synthetic division and the rational root theorem. Division, long division, and synthetic. Either way, find remainders. So I might give you some crazy problem to divide, but I'm not asking you to divide it. I just want to know the remainder. We talked about a shortcut to do it. You need to know the rational root theorem, including eliminating ones that don't make sense and leaving the remaining candidates. That's where the graphing calculator comes in. Create a polynomial. So that means I might say 2 is a root, 5 is a root. Well, if you know 2 and 5 are roots, you know x minus 2 and x minus 5 are factors. FOIL those out and tell me what the polynomial would be. Okay, so you have to know how to generate polynomials if I give you roots. And the roots could be real or imagined. But that's everything that's on the test.